Hello, this is Jeffrey Frankel with Solutions in Chemistry. Today I'm going to talk about titrations and questions in IB Chemistry HL Paper 1. These techniques will help you do these questions in less than 30 seconds each and get them right each time. Variations of this question come up time and time again in either Paper 1 or Paper 2. And if it comes up in Paper 2, there'll usually be a long calculation. In Paper 1, it's more a matter of understanding the pattern of what you're looking at. In this case, if you saw this and you're told that it's a weak base and a strong acid, you've got to go immediately to C, and that's the answer. Now let me explain how I got there and my thinking about that. As a general rule, in practical terms, strong acids and strong bases are usually used in titrations at a strength of 0.1 mole per decimeter cubed. So let's take a particular strong base, NaOH, 0.1 mole decimeter minus 3, and that's sometimes referred to as 0.1 molar. Let's take HCl as a strong acid. That would be usually used in approximately 0.1 mole decimeter minus 3, and it's again 0.1 molar. Now the pH of sodium hydroxide at this strength, pH equals 13, and the pH of HCl in this strength, pH equals 1. If you get a weak base, such as ammonia, ammonia is the strongest of the weak bases. The maximum in a concentrated solution of ammonia, the maximum pH will be in the region of 10.5. More likely the pH will be around about 10 or thereabouts. In the case of a weak acid, let us take CH3COOH ethanoic acid. In a concentrated solution, the pH will be around 2.5. More likely, the pH will be 3 or thereabouts. And with other weak bases, the pH will be less than this. With other weak acids, the pH will be higher than this. So there's a clear distinction between the pHs of ammonia and other weak bases and sodium hydroxide solution at a particular concentration, and between a weak acid, such as ethanoic acid and other acids, and hydrochloric acid at a particular concentration. Now let's go over to the curves. And if you look at this, you can see that the pH is around about 13 or thereabouts. Therefore, that is a strong base. That has to be a strong base. You look at this, pH here is about 1 or thereabouts. That must be a strong acid. And this curve is typical of a strong base, strong acid. This curve here with this very long line which goes from about pH 3 up to about pH 10 or thereabouts approximately. And in the middle, which is exactly pH equals 7, that is the equivalence point. Equivalence. That is the point where the quantity of base is equal to the quantity of acid in molar terms. So that's strong base and strong acid. Let's go over here. Again, we can see it's a strong base for the same reason, strong base. This is a weak acid. The diagram here is not that accurate. However, if you look at a weak acid, this point here, let me put it there. There. Usually a weak acid rises and then goes like that. That is the characteristic of a weak acid, whereas a strong acid is very straight at that. A strong acid is very level at that point. With a weak acid, it rises like that. And that will be 3, 4 or 5, depending on the weakness of the acid and its concentration. And you get this vertical thing which is shorter than this one and is higher, and the halfway point is pH is greater than 7, and that's the equivalence point there. So that's strong base, weak acid. Let me go over here, where again you can see this is a strong acid. Strong acid. And this is much lower than 14, it's in the region of 9 or 10, therefore it's a weak base. Weak base. And this vertical thing is, again, much shorter than that one, and halfway along is the equivalence point, and that is the pH is less than 7. Over here, this is clearly the fourth one, weak acid. Acid and weak base. Nobody would do a titration between a weak acid and a weak base because the equivalence point, which would be in the region of pH 7, it could be above it or below it, depending on the comparative weaknesses of the or strengths of the acid and the base. It's very difficult to see with any indicator, and even with a pH meter it's not very clear. What somebody would do would be a back titration, and I won't discuss this here. Back titration is something we will discuss in paper 2 questions, because that's where they come. The answer to the question is C, and it is important that you see these little aspects of these pH curves, the characteristics, and you remember these specific pH levels, so that these curves are not a problem for you. Having done that previous question, this one should be clearly easy. This is clearly a strong acid because it starts with 0, pH 0. 25 centimeters cubed of a liquid are added. And clearly, as the pH is increasing, this must mean that a liquid that is added is the base. And as the base finishes at, 9 or 10, thereabout, that is a weak base. So we know that's a strong acid, and it's a weak base. And the graph shows very clearly that the weak base is in the burette. Weak base in burette. So you go through here and you look for a weak base. Weak base, is in the burette, and strong acid in the pipetted into flask. That's the answer. Just as a comment on this, in general, the practice would be to actually put the acid, a strong acid, in the burette and the weak base in the flask. If you were doing this in a laboratory, you would put the strong acid in the burette and the weak base in the flask. And when you're doing a weak acid and a strong base, you put the strong base in the burette and the weak acid in the flask. With a titration of strong acid and strong base, it doesn't matter which way you do it. It's because of these. In this statement, they tell you that it's a known volume of strong acid. Therefore, the acid is put into the flask and the base is put into the burette. As the base is added, you know there will be an increase in pH. Steady increase in pH? No, it's not a steady increase. There's a sharp increase in pH around the endpoint. Yes, from the previous graph, we've seen that there is a sharp increase in pH around the endpoint. There's a steady decrease in pH, there's a sharp decrease. No, those are definitely not true because we are putting the base into the burette and therefore the pH will increase. When you look at this, try and think of which would give the highest pH at the equivalence point. You know that you're dealing with a strong base and a weak acid, and that's A. As we discussed earlier with the 4 graphs, if you have pH, that's 14, and that's naught, and that's volume, the highest pH at the equivalent point would come because the base is very high, it comes down, and it goes like that. and the equivalence point is somewhere along there, which pH is greater than 7. With a strong base and a strong acid, strong base, strong acid, the pH would be equal to 7. With a weak base and a strong acid, the pH would be below 7. So that's pH equals 7. That's pH greater than 7. That's pH less than 7. This one, pH, we don't know. It's around 7. But it's not going to be as high as that one. And it's not going to be as low as that one. So the answer to that is A. Having explained those curves in a previous exercise, we can see immediately this is a strong base. pH of 13 going up to 14, that's clearly a very strong base, a very concentrated solution of base at that point. And here we see that this is a weak acid. The pH starts somewhere in the region of 3. It has this move upwards, and then the gradual change over there. And then the vertical point where the acid is equivalent in molar quantities to the base, whatever that base is, which we've agreed is a strong base. Okay, and you can see that the equivalence point is there. Equivalence point. And that is clearly a pH greater than 7. That's the important thing. pH greater than 7 because there's a strong base and a weak acid. So let's look through these, and we're looking for a strong base, sodium hydroxide. And what also we need to realize is that because the pH is rising, therefore it indicates that the sodium hydroxide, if it is sodium hydroxide or other strong base, is in the burette. So here we go through here, we see aqueous sodium hydroxide is in the burette and ethanoic acid pipetted into the flask, and that's clearly the answer. It's a strong base, a weak acid, and the strong base is in the burette because the pH is increasing. None of the others make sense, and this is the only one that explains that curve. So when we look at this, we can see initially that this too is clearly a strong base. Strong base. And that's because the pH is about 13 or thereabouts. And this one is clearly a weak base because the pH is in the region of 11 or so. That's a weak base. It's quite a strong weak base, but it's still a weak base because it's the same concentration of that one. Both are the same concentration, 0.1 mole decimeter cubed, but this is a weak base in comparison to that. And when we go down here, we can see this is, well, they do tell us it's hydrochloric acid, so that's a strong acid. And the next thing we can see is that they don't tell you what is along here, but you can see that it clearly is the acid. The acid is being added through the burette into the flask. And the flask contains, in one case, strong base, and in the other case, the weak base. So that's, as soon as you see that, you can describe exactly what is happening. And then when you go through the questions, and you look at the answers, graph 1 is titration of a strong base. No, you know it's not. Forget it. Both graphs, the acid was pipetted into the flask. No, it wasn't. Graph 1 is titration of a weak acid. No, it isn't. Graph 1 is titration of a weak base. Yes. And graph 2 is titration of a strong base. Yes. And that's the answer. Once you've got to understand these curves, these pH curves, and you can interpret them, then these questions become easy, and you can do them within 10-15 seconds or so. Okay, we can immediately see that this is a strong base being added through the burette. This is somewhere in the region of pH equals 12 or 13, and the equivalence point is well above 7, so that the pH is greater than 7, and that here we have the very clear weak acid characteristic, and that is, what is that? That's 3.5, a pH of 3.5, perfect for a weak acid. So we're looking for a weak acid and a strong base. Ethanoic acid, that's a weak acid. Strong base, sodium hydroxide. Okay, so that first half of that sentence is correct. Ethanoic acid put in the flask and sodium hydroxide in the burette. Now there's this thing here. This is not true. The equivalence point indicates when pKa equals pH. I'll discuss that in a few minutes, but that is not true. That's not right. Ethanoic acid put in the flask, yes. Sodium hydroxide in the burette. And the equivalence point indicates the end of the titration. Yes, that is true. Sodium hydroxide put in the flask, no. Okay, so let's have a look at this. What exactly is this? The equivalence point is where the amount of, in this case, sodium hydroxide is exactly equivalent to the amount of ethanoic acid for the equation. Let's put the equation down. NaOH plus CH3COONA goes to, that's the acid. That is the acid, not the NaOH. Then that's aqueous. That's aqueous. And that goes to CH3COONA plus H2O. And that's aqueous. And that's liquid. Okay, so when the quantity of sodium hydroxide is exactly equal to the quantity of acetic acid, then that is the equivalence point. There is another point known as the half equivalence point, which is here. Half equivalence point, half equivalence. And it's simply determined by determining where the equivalence point is. Let's say that's 30 for convenience. Where the equivalence point is. Half would be 15. And there's no other way of determining the half equivalence point except by going to the equivalence point and halving the quantity of titrant that you've added. Now, in this case, the titrant is sodium hydroxide solution. Halving that quantity. And then you look at that pH, whatever that pH is. Let's say it's approximately 6.9. Let's say pH equals 6.9. Something of that nature. 6.9 or thereabouts. pH equals 6.9. Now, the thing is, what does this mean? This means that we have half the sodium hydroxide added, and half of that has been used up. So it simply means that the amount of sodium hydroxide added equals half the acid used up, and there is another half quantity of acid present. So what we can say is that if this is the ionization constant, or dissociation constant, whatever you'd like to call it, for the acid, and let's put the equation for the acid down. CH3COOH goes to, and that's a reversible equation, mainly in that direction, CH3COO minus plus H plus. There is the other way of writing this, where you put water there, and there's H3O plus, but it doesn't matter which way you do it. Let's do it this way. So the Ka equals the concentration of CH3COO minus times the concentration of H plus over CH3COOH. In this situation, what we have done, we have converted, with the sodium hydroxide, half of the ethanoic acid into ethanoate, and what remains is the other half of the ethanoic acid. So the concentration of that equals the concentration of that, because we have converted half of the original ethanoic acid into ethanoate. So those two cancel out, and Ka equals concentration of H+. Now we know that pKa equals minus log Ka, and we know pH equals minus log H+. So therefore pKa equals pH. Therefore pKa equals pH. So this pKa equals pH occurs at the half equivalence point and not at the equivalence point. If you're having difficulty with this argument, then it's possibly because you're unclear about logarithms. And as I've suggested before, get yourself a book on mathematics, look at the chapter on logarithms, spend 10 minutes a day for a month working through logarithmic exercises, and you'll find this type of problem very easy. It is essential because there's usually a logarithmic problem, certainly in paper 2, maybe not in paper 1, but certainly in paper 2, there's usually some kind of logarithmic problem involving either buffers or salt solutions or titrations or water and its various K values and pH values and so on. Make sure you are conversant with logarithms. Okay, so in this case, the ethanoic acid put in the flask, sodium hydroxide in the burette, as we've said, and the equivalence point indicates the end of the titration. If you found this YouTube video helpful, please subscribe to my channel and look at my other videos. Thank you.